Hello, everyone. I've had a couple requests to do an example problem with the CoolProp libraries that I sent out. So I'm going to do this one, 716 from the 8th edition, right? And the focus won't be necessarily how to solve the heat transfer part of this problem, with the energy balance and stuff. So I'm not going to go detail into that, but it will include a fair amount. And so let's see. In 716, in the 8th edition, if you want to look that up, I'll give you enough detail here, but if you want to look it up in more detail, it is 716. We have this refrigerator truck with some inside temperature, and they actually tell us that that's 263 K. This middle part is insulation, and essentially you just have two plates sandwiching the insulation. This is the surface temperature, which is what we're actually solving for. Okay, so since we're actually looking for the surface temperature, what we can do is we can draw a control volume around the surface and draw our interactions, right? So we have some alpha G coming in, we have some emission. Okay, we have some conduction leaving the system, going to the refrigerator. We have some convection. And I believe that's it. Okay. So we know U infinity is equal to 110 kilometers per hour, which is equal to 30.6 meters per second. We have a T infinity, which is 303 K. The emissivity, as well as the absorptivity, is equal to 0.6, at least for part A. And then you're given some other things to calculate the resistance. I'm just going to give the resistance here, since that's not what we're actually solving for, right? So we do our energy balance, E dot in minus E dot out plus E dot gen is equal to E dot stored, right? So we're going to say that this problem is steady state with no energy generation. So what comes in is what comes out, right? We can say alpha G minus E. Well, let me do this. So we're going to say this is E is equal to epsilon sigma TSO to the fourth. Okay, so alpha G, then we're going to have minus epsilon sigma TSO to the fourth. Okay, then we're going to have some convection coming in. So we know that that is H T infinity minus TS. And then minus the conduction going out. That's just going to be TSO minus TSI over. Oh, sorry, my pen is not doing well today. It's equal to 0. This is just the definition of resistance. Okay, so I'm going to highlight in green everything we know. We know alpha, we know G, that was given. Let me clarify that as 900 watts per meter squared. Okay, we're given epsilon, sigma is a constant, right? Where sigma is equal to 5.67 times 10 to the negative 8th. Watts per meter squared. Oh, I don't remember. The top of my head. That is Thinking about, oh yeah, I was right, watts per meter squared, but this is Kelvin to the fourth. Okay, we don't know H, we know T infinity, that's 303K. Let me clarify, this is TSO. TSI is 263, and I gave you the resistance. That is something you can calculate looking at the problem. So you'll notice that in yellow is everything we don't know, right? So we don't know TSO and we don't know H. So now we say, what is H, right? So this is when you follow section 7.3. So 1 is the geometry. In this case, it's a flat plate. Okay. 2 is calculate the reference temperature. So in this case, I'm going to calculate the film temperature, which is going to be TSO plus T infinity. It's just the average of the two. What you'll notice here, though, is that this is somewhat problematic, this TSO. And that comes because looking at this equation here, our energy balance, we can solve for TSO, and we get that TSO is going to be some function of H, right? And then H is some function of TSO. So effectively, we have TSO, the outside surface temperature, is some function of itself. So this is where our CoolProp is handy, okay? Because essentially what we have to do is we have to make a guess for TSO, okay? And then we're gonna have to iterate through this methodology of these steps, okay? So 3 is calculate Reynolds number. At the film temperature, right? So you have rho, U infinity, L. L in this case is 12. I'm gonna just put that here, 12 meters. Okay, and then that would be divided by the kinematic viscosity. The other thing, this is equal to U infinity L over nu. Okay, so this, and this are functions of reference temperature, right? So that's why you calculate the Reynolds number at the film temperature. Okay. 4, pick Nusselt correlation. So the purpose of calculating the Reynolds number 2 is to ask yourself, is it turbulent, laminar, or mixed? Okay. So come to Nusselt correlation, we have flat plate. And in this case, when you calculate out the Reynolds number, you get that it's turbulent, right? Okay, now you have to ask yourself, is it fully turbulent or is it mixed? So when I calculate out Reynolds number, I get, let's see if I can write this, okay. So I get Reynolds number is equal to 30.6 meters per second times 12 meters of the length. And that is going to be divided by 15.89 times 10 to the 6th, right? This, okay, just so you know, this value, because I'm trying to go through this a little quicker, this is something I pulled from the solution manual. So they make a guess of, let's see what they do. Okay, so they say in the solution, they say their film temperature is approximately 300K. All right, so it doesn't matter because if you iterate, it's going to converge. but this value right here won't change by that much. So I'm going to get that this is equal to 2.31 times 10 to the 7th. Remember that the critical Reynolds number for a flat plate is 5 times 10 to the 5th. So this is 2 orders of magnitude larger. So since it's so much larger, you can say that it's fully turbulent. Okay, so now I want you to go look in section 7.9, table 7.7. Okay, let's see. I'm gonna pull that up, or at least attempt to. Sometimes my Adobe crashes. Okay. All right, so come down here, section 7.7, summary, 7.9. All right, so you see this 7.7, we have a flat plate. We have fully turbulent conditions. So what you can do is you can use this equation right here. Okay, this 7.38. And then just so you know, in the book, it states that this is equal to 0 for fully turbulent. Okay. And then let's make sure we use the film temperature. We have to make sure we meet our conditions, our Reynolds number. So critical Reynolds number, that's right. And then our Reynolds number is less than 10 to the 8th. And then Prandtl for air, you can calculate it. It'll come out to be about 0.7 something. So that condition is also met. So all our conditions are met. So we can come back here. And we can say that the average Nusselt number is equal to 0.037 Reynolds to the 4/5 Prandtl to the 1/3. So remember that H bar L over KF is equal to the average Nusselt number. So we can say H bar is equal to 0.037 Reynolds to the 4/5, Prandtl to the 1/3, and I'm going to add K of the fluid here and L of the plate, right? So you're going to calculate this H bar, right? And then suppose you get 50, and that's watts per meter squared Kelvin, right? Now what we can do is we can come up to our equation right here. So let's copy that. Come back down here, paste that. So now I say suppose 50, that's not something you actually do, you actually calculate it, right? This is where you can use CoolProp here again. So we've used it at least twice. Oh, and then you can use it for here and here also. Right, so for example, let's say we get 50. So we can plug 50 in here, right? And now this is no longer yellow, meaning that we don't know it. It is now green. And now you see we have one equation, one unknown, so we can solve. So you're going to get TSO, and then let's say, suppose you get 307. Okay. What you want to do now, and we're going to change colors here to indicate we're going to a second iteration. We come up here, all the way up here to the film temperature, sorry, not to the Reynolds. So come up all the way to the film temperature. So we're going to say 2. TF is equal to, and now you say that thing that you just calculated, 307 plus T infinity over 2. And then you look at your Reynolds, right, at the new film temperature at, I'm going to say TF2 for the film temperature 2, right? And then we calculate H again. right? Run through, let's see, down to here. If we calculate H, so we say TSO is equal to, I don't know, well, you can say 306.5 maybe. So then you would probably do another iteration, right? So you would just run through this process again using the 306.5. Right? And then let's come all the way down. Sorry, and then let's say your TSO is now 306.4. You can see that it didn't change, and you can effectively say that the solution has converged depending on what you pick your tolerance to be. The tolerance being so it would be the absolute value of TSO n plus 1 minus TSO n, whatever that is, right? So now we're going to go over to our, I'm going to open up MATLAB and code this up, right? Because you can see where this really comes in handy with the CoolProp libraries is because your film temperature is changing, all of your properties change, right? So instead of running through this process by hand 3 or 4 times, you can put it in a while loop. Okay. Let's open up. Oh, I've already got MATLAB. Okay. Just a second. Okay. So what I'm going to do is start coding this up. So clear all, CLC, right? So then I do my initial guess input. So outer surface temperature guess is going to be equal to, and I would just pick something close to whatever the T infinity is, right? Because that's that'd be logical, right? So it doesn't matter what your guess is, but just try and make it logical. Now it has to be hotter than 263, but I know that the way I've drawn my convection, it would be cooler, right? And the signs will take care of themselves if I was wrong in that guess. So then I would do like my material stuff right here, and I would say alpha is equal to 0.6, epsilon is equal to 0.6, right? And then I would just say the Stefan Boltzmann constant, right, is going to be the sigma is equal to 5.67 times 10 to the -8. Then I'd have my environment conditions, right? So I would have the free, well, I'll just call it T infinity is equal to 303K. And then the velocity is equal to 30.6. Atmospheric pressure is equal to 101,325. I put the atmospheric pressure in here so that we can plug it in the CoolProp libraries. We have that the solar irradiation is equal to 900. Okay, so now I put in some geometry, and really like a lot of this organizing that I'm doing right now is pretty arbitrary, right? Like do whatever, organize it however best makes sense to you. So this was the thermal resistance of conduction, which can be calculated, but I just gave it to you to simplify the problem. Well, just because it wasn't something I wanted to focus on for this presentation right here. So now I'm going to set my tolerance value. I'm going to set it equal to 1. That's pretty arbitrary as long as it's greater than what you actually want it to be, right? And then I'm going to say for this first one, I'm going to say my outer surface temperature is equal to my outer surface temperature guess. Okay, then I'm going to do my while loop. Tolerance is greater than, I'm going to say once you're at a 1/10 of a degree, it's pretty much converged, right? So my first step is to calculate the film temperature, which is going to be the outer surface temperature plus the infinity divided by 2. Okay, the next step is to calculate Reynolds number, right? So I'd say my Reynolds number is equal to my density times my velocity times plate length divided by dynamic viscosity. So you'll notice I have a bunch of terms here I haven't defined yet. So let's define density. And this is where you can start using CoolProp, right? So you'd say pi dot CoolProp dot CoolProp. Okay, and we're going to go D for density. We want the density. Okay, and then your first known is, in this case, it'd be pressure, right? Atmospheric pressure. Your second known would be your film temperature, and your fluid is air. Okay, velocity is defined, plate length is defined, so dynamic viscosity is equal to same thing, pi dot CoolProp dot CoolProp EP atmospheric pressure T, same thing. I mean, this is exactly the same thing, except we changed, I wrote D here, I apologize. This should be viscosity, film temperature. Yeah, it's the only thing that changes. Okay, and then we need to put in our fluid here. Colon to suppress the output, right? So that'll calculate our Reynolds number. And then we can say kinematic, oh, sorry. So then what I would want to do is calculate the Prandtl's number, sorry, right? And we know that that is the kinematic viscosity divided by the thermal diffusivity. Okay, just wanted to take a moment. Again, there are some things that are kind of arbitrary here, like which definition you're using, because the kinematic viscosity is defined in terms of the dynamic viscosity, right? So technically I could have used Reynolds number using a kinematic viscosity, but the CoolProp libraries do not spit out kinematic viscosity. They only spit out dynamic viscosity and density, which allows you to calculate it. So I'm going to do it, leave my Reynolds number like this, and I'm going to do Prandtl's number using kinematic viscosity so that I can show you kind of how that works, right? So the kinematic viscosity, I know that that definition is the dynamic viscosity divided by density, right? So that's the fun. So now we have to say thermal diffusivity. So I'm going to say thermal diffusivity is equal to the thermal conductivity divided by density times specific heat. Okay, so again, we have some terms we haven't defined yet. So let's define the thermal conductivity is equal to pi dot CoolProp dot CoolProp dot props SI. Okay, and the symbol for this is L. Okay, and then again, our known as pressure, atmospheric pressure. T is the film temperature, and that's at air. Okay, and then looking at our thermal diffusivity, we haven't defined specific heat yet, so specific heat is equal to pi dot CoolProp dot CoolProp dot props SI, and this is C. Okay, and then we got P, atmospheric pressure, T, film temperature, air. Just double check, got a semicolon there. Okay, so that makes thermal diffusivity defined, which makes Prandtl's number defined. Okay, so now we plug in H, right? So we say H is equal to the, and this just goes back to that equation we wrote down, right? Where it was Kf divided by L. So we have the thermal conductivity divided by the plate length. Okay, and that was times 0.037 times Reynolds number raised to the 4/5 times Prandtl's number raised to the 1/3. Okay, so that gives us H. Okay, so now I'm going to say my outer surface temperature is equal. Now, I picked this one because solving for the surface temperature is a little bit more complicated because you have TS naughts and you have TS naughts to the 4th. So it's best to use, I think, a nonlinear solver, right? So I'm going to use fsolve. Okay, at X. I set this, the way I'm doing it now will kind of show you how you can pass in lots of variables, right? So you set kind of this dummy variable X for now, and then I'm going to call it my non-linear surface temperature solver. Okay, and I'm going to pass in X, which is going to be my guess. When I call in fsolve, is that how it works? Yeah, so just, so I'm going to need to pass in alpha, epsilon, G, H, T, infinity. Oh, whoops. Let me do it this way. All right, so I've worked this already, so I'm just kind of copying it. So I'm just changing the order just so everything stays correct. Infinity, epsilon, sigma, r double prime, inner surface temperature. Yeah, okay, that's right. So when I said passing this dummy variable X, it's because when you pass when you call fsolve, it's going to call the nonlinear solver, which has to take an initial guess, right? So then let's see, so get rid of that and then go comma outer surface temperature is the guess. Okay, and that's all there. So I'm going to save this as my main, right? So I'm going to call this main surface temperature. And then remember this one over here, I'm going to save it as this, right? So save this nonlinear surface temperature solver. Okay, so now what I'm going to do is I'm going to say function. I'm going to say my outer surface temperature is equal to my nonlinear surface temperature solver. And I'm going to pass in the values in the order that I wrote them in the main surface temperature, right? Leaving out the X. So you say outer surface temperature. So not leaving out the X, but replacing it, right? So outer surface temperature, alpha G H T infinity, epsilon, sigma R double prime, inner surface temperature. Okay, make sure you end that. And now we plug in, we just plug in the formula we did as long as it's equal to 0, right? So we can say the outer surface temperature is equal to alpha times G plus H times T infinity minus the outer surface temperature minus epsilon times sigma times outer surface temperature raised to the fourth minus outer surface temperature minus inner surface temperature divided by R double prime. All right, so there we go. Let's save that. Let's save this. Now there's something I haven't done yet. I've said, well, my tolerance is greater than 0.1, and at the moment it's always greater than 0.1, so I need to make a reassignment here. So what I'm going to do is I'm going to say T tolerance, and I'm going to set that equal to the outer surface temperature before I reassign it, right? Because then I call outer surface temperature. And I reassign, I make a new value for that, right? So what I want to do is I want to say tolerance is equal to the absolute value, and that's going to be T tolerance minus the outer surface temperature. All right, let's save that. Let's see if it runs. At least one end is missing, which is here. Here we go. Okay, undefined variable pi. Oh, so you'll notice here I missed my dot props SI in line 32. CoolProp.CoolProp.props SI, and then here dot props SI. Yep. Okay, let's see. Velocity. Did I not? Oh, it's because I did it with a capital here. So line 34. We'll just do that. Make sure there was no other instances of me. Yep, okay, perfect. Using that. Okay, yeah, so it ran. And actually what I would probably do, just to make it easier, is I would just print the value once this loop has stopped. Oh dear, outer surface temperature is equal to 0. That's not right. So, let's see. I'm gonna just double check this. The outer surface temperature equal to alpha times G plus H times T infinity minus outer surface temperature minus epsilon sigma outer surface temperature raised to the fourth minus outer surface temperature minus inner surface temperature. Okay, that all looks good. Yeah, let me just double check some of this. Okay, H is thermal conductivity divided by plate length, 10.037 times Reynolds number to the 4/5 times Prandtl's number to the 1/3. So let me make sure. So H is getting defined here, right? Let's see, what was my guess? Yeah, 0.6, 5.67 times 10 to the negative 8, T infinity, velocity, atmospheric pressure in pascals, 900 watts per meter squared, 12, 1.923, inner surface temperature is 263. Yeah, so let's see, H is equal to 85, and then I say tolerance is equal to outer surface temperature is equal to F solve at X, non-linear surface temperature solver. And then it's possible that something here is getting mixed up. X alpha G H T infinity epsilon sigma R double prime inner surface temperature, then the guess is outer surface temperature. And then reset the tolerance. Okay, so let's double check this. We've got the outer surface temperature, and we should have alpha G H T infinity epsilon sigma R double prime inner surface temperature. Okay, so I'm going to pause the video and try and debug this so I don't make the video super long. Just a second. Okay, I figured out what it was. I apologize that I just misspelled this. Temperature. Now it's all good. Control S, run. 306.8342. So there you have it. So let's kind of summarize what we did. We started the problem. We drew an energy balance. Well, we drew a control volume, the interactions with its surroundings, used the energy balance, got this equation, realized we had one equation, two unknowns, but that we can solve for H. So we started solving for H using section 7.3. So we have a flat plate. We have to choose a reference temperature. So we use, in this case, we use the film temperature, which is the surface temperature plus the infinity divided by 2. So make a guess right here, right? So make a guess, calculate the Reynolds number. For the initial, before you pick the correlation, you have to do this one by hand, or just not within the iteration so that you can see what you're doing. So I got that it was pretty big right here, right? So Reynolds number is turbulent and it's 2 orders of magnitude larger. So I said that it was fully turbulent and used this equation from the book, 7.38, realizing that the book says you can simplify this equation by saying that that is 0. Okay, now let's see. Solve for the Reynolds number, solve for the Prandtl number, solve for the Nusselt number, solve for H. Plug H in, and then I use a nonlinear solver to solve for TS. And then I wrote a while loop to just iterate through that, right? So let's, okay, yeah. So a couple things I want to show you guys. One thing is I had this extra term right here, maybe, yeah, see that? I realized I had this term when I had stopped. I didn't get rid of it after debugging, right? So just delete that. You don't need that. You can see that the solution is still good, right? So what I wanted to show you is, say you didn't know that you could set the 871 to 0 for fully turbulent. Like, I guess the question is like, how much of a difference does it make? So setting it equal to 0, see that you get 306.83. And then if you add it, 306.94, right? So it changed 0.11 degrees. Really isn't that significant of a difference. So, you know, for you, if you want to just always leave the 871, because if it's fully turbulent, then the Reynolds number largely takes care of that, and it's really not that significant of a difference. That's probably fine, just so you know. The other thing I wanted to show you is, does the guess matter, right? So right now we have 306.94. So let's change this guess to 300. Do we get 306.9470? Pretty darn close, 306.9473, right? Let's change it to 500. 306.9474. Okay, what if we do 800? 306.9474. 200. 306.9474. 100. 306.9474. So you can see that your guess, if you do a code, your guess really doesn't matter. You should definitely always make a logical guess. Like making a logical guess, I would never guess that the outer surface temperature is 100, right? That doesn't make sense the way we set up our problem. It's a refrigerator, which means heat would be flowing the other way, right? So that's why I say my guess, I would want it to be between 263 and 303, you know. So you could do 299 or whatever you want to do. it comes out to be the same. The thing is, if you do all of this by hand, you want to guess close, right? Because if you guess 100 here, it's going to go through more iterations than if you guess if you guess 306, it's probably only going to have to do 1, maybe 2 iterations. So if you do it by code, your guess really doesn't matter. If you do it by hand, it's definitely time consuming to guess very far off. So always make a logical guess. That's best practice. Make a logical guess. Okay. So again, we look at our problem, right? We do an energy balance, 1 equation, 2 unknowns, solve for H, make a guess for T initial, use Reynolds and Prandtl, pick a new salt correlation using table 7.7 and section 7.9. Calculate all those numbers, calculate H, use H, calculate TS naught. If you don't have this raised to the 4th term, you can probably separate terms and get a linear relationship, right? But because of this 4th and because of the 1s, I use the nonlinear equation solver, which I showed because you might have that for your project or for future problems, right? And that shows you how to use a nonlinear solver to solve for the temperature. And I call that within the while loop so that I can reassign the tolerance. So I reassign the tolerance value, I reassign the surface temperature, run through the same thing again. And I just tell the while loop to keep going until the solution converges. So anyways, there you have it. I hope it helps. If you need any more information or anything else I can do, let me know. Have a good day, guys.